This week we're talking about the separation of gas. So basically today we're talking about two different processes. One is adsorption and one is absorption. The only difference here is one letter, the D or the B. Make sure you know the difference by the end of this lecture. The first we're going to talk about is adsorption. So in adsorption, gas is attracted to a surface, usually of a solid, could also be a liquid, and it's separated from the airstream. And it takes place at the interface of the adsorbent and the adsorbate. So here you see an example. The adsorbent is the material that is binding something, and the adsorbate is the molecules here, when we're talking about air pollution, that come out of an airstream and are fixed to the surface of this adsorbent. And here this is shown just as a round particle, but in reality, the amount of material that this adsorbent can bind to it depends simply on how big the surface is. And so these particles are usually not solid, but rather they're filled with tiny pores and channels that break down into smaller and smaller channels, so that inside these adsorbents there's actually lots and lots of surface area. So it's not just the surface of a sphere, but if you spread it out, it can cover a huge field. There's some common physical adsorbents, for instance, activated carbon. In case you see me on the camera, I don't know if you do. Here's some activated carbon. Silica gel. You might know silica gel if you buy shoes or a leather purse or something. This is added to it. It's this material. It's made from sodium silicate, which is then treated by acid. Activated alumina, aluminum oxide is also can be activated and used to absorb moisture. And there's also some kind of ceramic-looking particles, aluminosilicates, commonly referred to as molecular sieves. Okay, back to common physical adsorbents. So here are some that I have sitting around just as examples. The first one I mentioned was this activated carbon, and maybe you've seen this. So if you buy a water filter, like a Brita water pitcher, so that you have really good clean tasting water, those filters are actually filled with activated carbon. Or if you happen to have an aquarium, which is maybe unlikely when you're a student because they're a lot of work to move, but if you like fish and have an aquarium, also activated carbon is used to clean the water. And this is by far the most common adsorbent. So it's not just something that you use for water and pets, but this is used in really huge amounts industrial for absorbing pollutants. I did an internship at Prex Air, for instance, and they would use this to absorb mercury. It has pore sizes that have a pretty large range of sizes, so from 10 to 10,000 angstroms. And as I showed before, there's kind of these pore networks, and so you'll have large pores that lead to small pores in different sizes. And in principle, per gram, you can have surface areas of 500 to 1,500 square meters. So if you think about, if you happen to visit my office, this time I only have virtual office hours, it's a really big office. It has a surface area of about 25 square meters. And you can see these numbers. So this is like 10 to 100 times the size of my office. So almost the entire building I'm sitting in, this kind of surface area is packed into 1 gram of this material. Super high surface area. Okay, when we're talking about activated carbon particles, therefore, one thing we'll need when we start doing calculations and designing these kind of filters is how much material goes into the filter. And since these are highly porous materials, it's not just the density of the carbon, but it's kind of the effective density of the material, how much carbon is actually located in 1 cubic centimeter. And since it's so porous, it's not that much, and it depends a bit. So here I have activated carbon pellets. If you're using this kind of granular material, it'll have a density of in 1 liter, somewhere around 0.22 to 0.5 kilograms. You can also get this in the form of a powder, in which case the density is is higher. And in reality, the density of the carbon material would be 2 or 2 kilograms per liter. But just because it's mostly air inside of these particles so that there's lots of space for the pores, the bulk density is much different. So make sure when you're doing these kind of calculations, you keep in mind what you want to know is the total amount of material. I can't do anything about the sound. I'm really sorry, and I hope it's better next week. Sorry, guys. The granules can be packed. Maybe I'll go a little faster and we'll try and hit the main points. If everyone agrees, since apparently the sound is not very fun to listen to today. Okay, so you have this kind of material, and the size doesn't tend to affect the absorption, but it affects just how it's packed into a container. And so in small containers, you might pack powders, and these kind of pellets are really common. Okay, this molecular sieve material you can see here, and in the sides you can see these are kind of particles like ceramic, and this is a defined pore structure, the way that they are made. And all of these pores have exactly the same diameter, and by choosing different molecular sieves, you can choose ones with different pore sizes. And these can be used to absorb gases, in some cases ammonia or water, if they have a really small pore size of about 30 angstroms. If you increase the pore size to 40 angstroms, then these types of materials can be used to absorb CO2, SO2, and H2S. So for adsorption, the basic steps is first, the gas molecule has to get transported so it reaches the surface of one of these materials, and it needs to find the surface. Larger particles require longer transport times before the gases have diffused into the pores, and for very large molecules, they might not be able to enter the pores. Then through affinity, the adsorbent binds the adsorbate. This is a really important parameter for the process. We're not going to talk about the design. And both of these parameters, the surface area and the affinity, affect how much this adsorbent material can absorb. So let's talk about equilibrium. We already mentioned chemical equilibrium, and as I told you then, we're going to talk about it again in this case. This is a function of the temperature, and I would now like to switch to another document to show you. So I assume that you're still viewing my screen, and I hope that you can see a kind of handwritten PDF document. This is what you should see. And what I'd like to explain to you here is we're going to talk about two isotherms. So here, isotherm, the first one is from Langmuir, and the second one is from Freundlich. And I want to discuss how they describe this phenomena. So here are some sites in the adsorbent material. So each of these should be a site where a gas molecule could potentially bind to the surface of this material. And here are some molecules floating around in the gas, which could come and bind to these sites. So here's one molecule that's come, it's bound to the site. That means here in my picture, there's still 3 more sites where 3 more molecules, if they came and made contact with the surface, that they could bind. This reaction can then be described as the gas, so the concentration of the molecules that should be bound, react with one of these sites to form a new entity, which is a gas molecule bound to the site. Okay, now the number of sites initially is here, M, denoted M, and there's a maximal number. And at equilibrium, there's a certain number of sites that are occupied. So the number of sites available is the maximum minus those that are occupied. And this is an equilibrium value. You can kind of imagine, like, if the pressure is higher or the concentration is higher, that then in tendency, more of these sites will get bound. Okay, so this is the basic setup. when we're talking about the Langmuir isotherms. This depends on the pressure, this depends on the concentration, and so this equilibrium value, the mass of the material that is bound, depends on the concentration, the temperature, and the pressure. And so typically this value is given as grams per gram. So gram of gas material that's getting absorbed divided by kilogram or 100 grams of adsorbent material. Okay, the assumptions of the Langmuir isotherm are first that this adsorbed layer is made up of a single layer of molecules. Second, that adsorption is a reversible process, that the molecules combine, but they can also, the reverse reaction can also occur that they leave the site. Third, the process is dynamic. So the adsorbed molecules, they do not move on the adsorbent, but they may leave the site and re-enter the gas stream. And also that the enthalpy of absorption is the same for all of these molecules, and it's not changing with the concentration on the surface. And for this work, Irving Langmuir was awarded the Nobel Prize in 1932. Okay, so back to this isotherm which he derived. We have here these two, the forward reaction and the reverse reaction. And if we describe these in terms of the kind of a reaction rate based on the concentration, then the rate going backwards is proportional here to this M equilibrium. So here KL is the Langmuir equilibrium constant, is equal to this reverse rate times the forward rate, which would be C, denoting the concentration of the gas, multiplied here by the number of free sites, which is M, the maximal number minus the equilibrium number. Okay, so this is how we get from the assumptions of the model to the definition of the Langmuir equilibrium constant. Now I'm going to show you how this equation is typically rearranged. So this equation can be rearranged. M max minus M equilibrium divided by M equilibrium then is equal to 1 divided by here, the constant times C, the concentration of the gas. M equilibrium divided by M equilibrium is 1. So this yields M max over M equilibrium minus 1 is equal to 1 divided by KL times C. And this 1 can be added to the right side. So adding 1 here. And in the denominator there is KL times C. So this 1 becomes this KL plus C plus 1 divided by KL times C. Okay, this is the maximum divided by the equilibrium. Now this expression can be further rearranged. And here it's going to be rearranged so that we have C divided by M equilibrium. And this is equal then to placing this term in the numerator, 1 plus KL times C divided by M maximum times KL. So you can see both of those at the same time. Rearranging this expression, then we get this term. And now this term can be written as a linear function of the concentration. And the way this is done is here we keep C divided by M equilibrium and say this is equal to, now this KL times C divided by KL times M max. So these terms come into this part. The KLs cancel out and we have C, the concentration, divided by this M max plus 1 divided by KL times M max. And this equation is a linear expression. So here this M equilibrium is Y. M would be the slope of the line, would give us the value of M max. X is the concentration. So if we're changing the concentration of this species, and B would give us the intercept, gives us KL. And that's how, if you take this material, so you take some of this activated charcoal and you place it in a chamber with a gas and you measure just its, for instance, its weight change, how much of this material adsorbs to the surface, and you increase the concentration again and measure again how much adsorbs to the surface, and you can plot this kind of graph and fit these two parameters. Okay, there's one alternative for this expression. You can also divide each of these terms by C, by the concentration. And in this case, instead of having a line in terms of C, the concentration, you get a line in terms of 1 divided by C. And this is how this expression can be linearized. So in the model of Langmuir, in the derivation, we said the rate of absorption is equal to the rate of desorption. We set these two rates equal to each other, and then we solve this expression in terms of M equilibrium and M max. The Langmuir constant is then defined as K1, the forward rate constant, divided by K2, the reverse rate constant. And when we write this in the form, then we get for this expression that M equilibrium divided by M max. This can be seen. So M max would be the total number of sites. Initially, if at equilibrium none of them are filled, we have a value of 0. When every single one of these sites is filled, then we would have a value of 1. So that's why on the y-axis, this value varies from 0 to 1. And this changes with increasing the concentration. And you'll see it's not linear, but initially it increases much more rapidly. And at some point, as most of these sites are getting filled, it's just not likely. We said that one of the assumptions is that the molecules need to somehow find their way and bump into one of the free sites to get absorbed. As most of the sites are filled, this no longer happens, and so this curve tends to flatten out. So the Langmuir isotherm is a completely theoretical model. So we discussed the assumptions, they're very basic, and the mathematics are derived directly from this type of model, and this is what the curve looks like. Okay, and as mentioned here, I showed you how these equations can be rearranged into linear forms. And these linear forms are what is used for measurements, which help us to derive the parameters that describe the adsorbent material. Okay, the Freundlich isotherm is the second isotherm I'd like to talk about. Now, compared to the Langmuir isotherm, the Freundlich isotherm is pure empirical. That means there's no theoretical considerations, there's no assumptions. It's just a measurement, and you fit the measurement because that's what it looks like. So here there's also a similar curve. Increasing the concentration causes more of this molecule to be bound to the adsorbate, and this M equilibrium, so the mass, the grams of adsorbate per gram of adsorbent, increases in some kind of function, usually not linear, some kind of curve that looks like this. And this is simply fitted. So this can be done in a log-log plot. The Freundlich isotherm describes M as just a function K, Kf. So KL was for the Langmuir adsorption constant. Kf here refers to the Freundlich constant, multiplied by the concentration raised to some power of n. So taking the log of each of these terms means that if this curve was plotted on a log-log plot, then you would get some kind of line, and the slope of the line gives you here this term n, and the intercept gives Kf, the Freundlich isotherm constant, equilibrium constant. Okay, so those are the two models to describe adsorption. The Langmuir isotherm has some theoretical basis, whereas the Freundlich isotherm is just purely empirical. And don't forget the assumptions of the Langmuir model. These are not made in the Freundlich. In principle, the Langmuir isotherm works very well for single components and high concentrations, and the Freundlich isotherm is better for mixtures and low concentrations. Okay, so if you're going to solve a problem, adsorption with activated carbon, you know the theory, but doing the calculations is something else, and you can practice this in the tutorial problems. For this, you need to know, okay, you'll have some size of a container and need to figure out some mass of activated charcoal or some other adsorbate that could be packed into this, and then calculate probably how much pollutant could be absorbed by this kind of device. So the type of tables and the way you find this data is usually based on measurements. And for instance, here from Freundlich, you have M equilibrium in this log form. And this was extended by Yaz, and he added an extra term to make it fit better. So you have the log is equal to the constant A, B times the log of the concentration plus D times the log of the concentration squared. These coefficients are determined experimentally. And again, M equilibrium, always check the units. In your book, it's grams per 100 grams of material. In other books, sometimes the units are slightly different. So it could vary by a factor of 10 if it's per kilogram. And C is the concentration of the gas. So here's a table, here's an example taken from your textbook with these coefficients of A, B, and D for the Freundlich isotherm for different gases on activated charcoal. So say you want to adsorb propane, you have here the values of A, B, and D. You plug them in, here A, B, and D, into this expression, and then for the concentration, you can calculate just from this simple empirical expression how many grams of propane the activated charcoal could hold at equilibrium. And as a note, when you're practicing these problems, also for the exam, to save a little bit of time, in many engineering processes, you can ignore this last term that was introduced to increase it increases the accuracy of the model a little bit. But here, for instance, I calculated an example with N-butanol. And if you ignore this third term, the only difference is it's like 2%. So if you're in a hurry and just want to use A and B for your calculation, this is always fine. Okay, so let's say you have a filter. And keep in mind in this course, filter is a kind of general term. And don't get confused. So today we're talking about a filter, and actually if you pack one of these, if you pack activated charcoal or one of these adsorbents into a filter, the process is adsorption, and this is caused a filter. But there are different types of filters. There's also fabric filters, and they're more commonly also just called filter. So if you think like of your vacuum cleaner that has, or these face masks that we should all be wearing right now if we have contacts, these are also filters, and this is the most common use of the term filter. So when you encounter this term, try to think what kind of filter could be meant here, and don't get confused between one or the other. It's a pretty general term. So today the filter we're talking about is one that is packed with this kind of material. And so here you have an example. Here could be a tube, and it's packed with one of these materials. And so from this side, we have some air entering that contains a pollutant, and it starts coming into contact with this material. This blue line shows then how the concentration decreases. And say this yellow stuff is the pollutant. At the beginning, it has a high concentration, comes into contact with this adsorbent material and starts to get bound, and therefore the concentration decreases, which means also that the affinity according to the isotherm, that less of it, there's less of a concentration, so the driving force is less of it will get bound. It will take a bit longer, but it has this whole length of the column, so there will be many more free sites in this area where nothing has been absorbed yet. So the concentration is decreasing, but there's a higher availability of sites, and there's still some excess length here to make sure that all of these molecules get absorbed before the end. Okay, so this happens at the beginning when the polluted gas stream starts coming into the filter, and pretty soon all of these sites at the beginning are going to get filled up. And after this happens, this whole area, this part where the concentration is decreasing from 1 to 0, is simply going to shift to the right. And it's going to keep doing that. So pretty much this curve, its steepness will always be the same. It depends on the flow rate. But it's going to move just along the length of this filter. And this means that to the left side of this wave, wherever it occurs, the adsorption wave, that most of the sites are already occupied, where the sites are free, the concentration is decreasing rapidly, and to the right you have mostly unused filter, which has only been in contact with the clean air. Okay, and that's this concept of the adsorption wave and how the pollutant is absorbed in this type of filter. Okay, so here's a length, and delta tells us the width, how wide the adsorption wave is, and it's moving then step for step along the length of the filter. And at some point, so at some time, Tx, this distance is going to overlap with the end of the filter, and this is the breakthrough time. And this is the time at which some of the pollutant starts to escape from the filter. And so this depends on VAZ. This is the velocity of the adsorption wave. So this thing is moving along the length in some, probably not meters per second, but maybe millimeters per second as it's filling up. And you take the length minus the width that is occupied by this wave divided by the speed at which it's moving, and this will give you the time at which the pollutant starts to break through and come out of the filter. So one important question then, we know we have tables to get this M equilibrium, the amount of gas pollution that an adsorbent can bind, but how do we get this velocity, this speed at how quickly this wave is moving along the length? So we can do this pretty much just with the information we've given, and our basic approach is that we construct a mass balance. Okay, so in our mass balance, we have here a certain concentration and a certain flow rate in cubic meters per hour of air containing pollution that's entering the filter. Here, for this given concentration, everything is in equilibrium, and so all of the sites are filled at the equilibrium level until it reaches a certain slice, and here it's decreasing then where the absorption wave occurs, and over time this wave is moving to the right, so step for step. So the mass balance says, okay, we have this much stuff going into the filter device, into this slice. It's the flow rate times the concentration times this step of time, and it is equal to this equilibrium concentration, so the amount of material that the filter can bind, times the density, the area, and the velocity divided by time. This is basically a volume, but per time, which is being consumed and being used to bind the pollutant. Okay, in the mass balance, Q is the volumetric flow rate of the air, cubic meters per second, and equilibrium, again, is kilograms of adsorbate per kilograms of absorbent. Check the table when you use it. This is the concentration in the air. This is, you'll have to pay attention to the units here and make sure that it matches up. So what you need is usually kilograms of adsorbate per cubic meters of air, so that the mass matches up with the units of this term. If you're given ppm, then make sure you go and convert these volume and mole fractions into mass fractions. The density of the adsorbent material, and here the effective density, so not the 2 kilograms per liter, but rather the 0.2 kilograms per liter, the actual amount of material that can absorb. A is the cross-sectional area, and VAZ is the moving speed of the adsorption wave. So in practice, we know most of these values. We know the density, the area, the flow rate, and the concentration. These are problem parameters that should be given to us, or as an engineer, we could say, okay, this is the cross-sectional area of the filter that I'm going to build. We need M equilibrium out of the table. And if we have that, then we can easily rearrange this equation to get this velocity term, the speed of the adsorption wave. So rearranging this equation gives us an expression for VAZ. Okay, once we have this velocity, as we mentioned, there's a certain time at which breakthrough will occur. So a certain time when the first molecules here will start to reach the end of the filter and they're not going to get absorbed, they're going to start coming out of the system. We need to know this time because this is the time when we can operate the filter. So we're not going to operate the filter until it's completely full, but we're going to quit using the filter when it's helping us reduce the air pollution. So you'll remember from your first tutorial that usually the laws say you can't admit a concentration above this point. And so what you'll do is calculate, hey, when is our filter going to start letting through unacceptable amounts of air pollution, and make sure it gets replaced before that point occurs. So the weight almost reaches the end, but not quite. At some point, the penetration concentration, so this part of the pollutant that's not getting absorbed, will start to exit the filter, and this breakthrough point then is defined. It can also be defined as a ratio of the outlet to inlet concentrations. It's not always a concentration, but we'll see in the equation that's commonly used, it's set as a ratio. So when 1% of the inlet concentration escapes, or when 1% or 10% escapes. So 1% is a really typical value that simply you say, okay, I want to know the time it takes until 1% of my pollutant starts to escape. And the equation that is used for this is, we're not going to derive it, I'm just going to show it to you. It's the Wheeler equation for the breakthrough time. It's also using this assumption about the wave and the way it moves through the filter. And it says, okay, here Tx, this breakthrough time, is a function of a lot of things we know about the filter. And it's written in terms of a ratio. So C0 is the inlet concentration and Cx is the exit concentration. And so Cx could be set to, for instance, 1%, then this would be 100 divided by 1. You would have here ln of 99. So you'll specify this ratio, and these other parameters come pretty much just from things you know. M equilibrium, the capacity of the adsorbate, the gas volumetric flow rate in cubic meter per second, the inlet concentration. W here is the weight of the adsorbent, so in kilograms. If you have the density and volume of the filter, you can easily convert to the weight. The density and the flow rate divided by here, this mass transfer rate coefficient. This is the only thing that you're going to need to be given, as this will have to be given to you in the problem to solve this. Okay, so have a look at the adsorption tutorial problems, and we'll discuss this in the future. Now moving on to absorption. So this is now absorption with a B, and pay attention that you know that this is a different process than adsorption. But absorption is a volumetric process where the gases go into the structure of the solid or the liquid. And to tell the truth, absorption is it's usually a liquid, could also be a solid that somehow chemically reacts. Sometimes reaction is involved, but today we're just talking about the physical process that, for instance, a gas molecule, SO2, comes into contact with a droplet of water and it enters the water. It's now mixed within these molecules. This occurs mostly through diffusion and mass transport. And here this is governed by Henry's law. And Henry's law describes the equilibrium at the gas-liquid interface here at the surface. And it says that if you have a pressure and a mole fraction in the gas phase, that at this interface you'll have a certain concentration in the liquid phase, which is the Henry constant multiplied by X. And the Henry constants are also determined from measurements. This is something I measure in my lab, in my projects, just to say it's simply a property of the materials. For air pollution control, there are both physical and chemical absorption processes. And in physical absorption, like this water and SO2, it's simply physically absorbed. So if you have CO2 or air, if you have a bottle of water and leave it sitting open to the atmosphere, the air will simply diffuse into the liquid. If you stir or shake it, it will happen a bit more rapidly, but this is simply physically bound. This is one of the most frequently used methods for removing water-soluble gases. So especially these gases called the acid gases. Acidic gases such as HCl, and also like SO2 is forming an acid in reaction with water, H2S, CO2, this is also considered to be an acid gas, not considered to be air pollution, but just so you know, these can be absorbed in water very efficiently. Chemical absorption is used then for absorption, where the gas is brought into the liquid and then it even chemically reacts. And this helps that with physical absorption, at some point the liquid is going to be saturated and reach equilibrium. By adding a chemical reaction, you can actually you can hold more of this gas, and since the liquid can hold more of the gas, this increases kind of the concentration gradient that drives this process, and so it also makes it actually faster to absorb the gas. And this is used frequently, so for these gases, SO2 and H2S. Okay, I think you have one problem related to absorption in your tutorial problems. This is mostly just a basic mass balance then. So in your absorption tower, hopefully in your bachelor studies, you discussed that there's some advantages of a countercurrent contacting scheme over co-current, which is why we're just going to discuss the countercurrent contacting scheme here. But in principle, for the mass balance, the gas flows into the reactor, and the gas flowing in is usually air with some concentration of pollutant like SO2. It's contacting a liquid within this column, and so when the gas flows out of the column, it has a reduced concentration of pollutant. Liquid is flowing into the column. Liquid comes in with usually no pollutant in it. It absorbs the pollutant, and then it leaves with a certain concentration. So the mass balance says that the amount of material that leaves the gas stream should be equal to the amount of pollutant that is taken up in the liquid stream. And this can be written then. So in the gas stream, the amount of pollutant coming in is the concentration Y0 times G, the gas stream, is the flow rate going in minus what comes out. Here the mole fraction going out times the molar flow rate exiting the reactor, and this is equal then to the liquid. So the liquid going out contains pollutant, and the liquid coming in does not contain the pollutant. So, and in principle, if you can make a mass balance like this, you're already able to solve these types of problems, but the way your book does it, I'm going to show some extra steps, some extra equations in this process. Okay, when we're talking about air pollution control, we don't just have a pure gas, but it's usually the case that we have like an airstream or some gas in a high concentration, and we'll have just a small quantity, so some percent or parts per million of a pollutant that needs to be removed. And so in this case, the gas phase includes both the carrier gas and the soluble gas is the gas that's going to be removed. And so in the case of SO2, G, the total amount of gas phase would be this fraction of inert gas plus the fraction of the gas that should be absorbed. So the mole fraction of one and the mole fraction of the other multiplied by the total flow rate. So for instance, if you have 1 mole of SO2 and 9 moles of air, then in sum you have 10 moles of gas, and the fraction of the inert is 9 moles, 0.9, and the fraction of SO2, 1 mole divided by 10 moles is 0.1. So this would be the mole fractions and the total amount. In the liquid phase, you can construct a similar balance. So if you have 1 mole of SO2 divided in 9 moles of water, in sum, L, you have 10 moles of water. The inert amount is 9 moles, 9 divided by 10 is 0.9. 1 mole of SO2 divided by 10 moles. Total gives you a mole fraction of 0.1. So if you want to determine the total amount of the gas or the liquid, you can also rewrite it. So then the amount of inert material, it's not getting absorbed, it simply passes through the reactor. These remain constant. And so you can also write that that this G is equal to the amount of inert divided by 1 minus Y, where Y refers to the concentration of SO2 or of the pollutant. And the same thing can be done for the liquid. Okay, so if we use our balance equation and these definitions that for the total amount of the gas in the liquid, since the amount of inert is constant, then here we can write, okay, this first term, Y0 times G0. G0 is actually G inert divided by 1 minus Y0. So this becomes the flow rate of the inert gas, and here 1 minus Y0 gets substituted. The same thing for this Y1 term. We have Y1. G1 would be the inert amount divided by 1 minus Y, the concentration at this point. So we can rewrite this term. And we can do the same thing for the liquids, rewriting these terms. This equation can then be rearranged. So here, collecting the flow rates of inert and collecting these different mole fractions at Y0, Y1, X0, and X1. Okay, so this is the expression that was previously derived. If we assume that we have a diluted solution, so which is usually the case, that there's a low concentration of pollutant both in the gas phase and then also in the liquid phase, then we can also say, when we're looking here at these 1 minus Y terms, that actually this is essentially equal to 1, just because they're quite small. And if we just ignore everything in the denominator and say it's close enough to 1, we're anyway just working with ppm, then we get that Y0 minus Y1 times G inert is equal to X0 minus X1 times the amount of inert liquid. So here this is rewritten. These ratios of the changes in the mole fraction is equal, proportional to the amount of the inert of each substance of the liquid and of the gas. So, and this is then the liquid to gas flow ratio. This is also a convenient way to write this equation, because it tells you, okay, if you specify how much you want to reduce the concentration, so you say, okay, what the concentration reduction should be in the liquid phase, what the maximum loading capacity is of the liquid phase, then through this ratio you can calculate, okay, I need whatever. A 1-to-1 ratio would be just the same amount of liquid as gas, or less, or 40 times more liquid than gas. And this will help you to decide what kind of contacting device you need. Okay, this shows the Henry equation. So on the x-axis, there's the liquid phase mole ratio. This is the concentration in the liquid phase. And here on the y-axis, there's the mole ratio in the gas phase. So this says if we have any concentration X, then according to Henry's law, at equilibrium, we should have a corresponding amount Y. Okay, but when we actually run these devices, we tend to not have equilibrium. But we have a certain amount of gas, and it doesn't necessarily completely saturate the liquid. So the actual operating line is going to be shifted and will lie somewhat here to the left of the actual equilibrium line. And this is actually then, this difference is related to the rate of mass transport. And so these different operating lines show the performance of a given device. But in principle, yeah, if you want to reach equilibrium, you'd have to leave the things in contact for forever, and this is not practical. So there's some gap, some difference between the actual rate and the equilibrium condition. So to deal with this, there's expressions written. This is the rate of mass transport, and there's a mass transport coefficient for the gas phase here, and for the liquid phase kx, multiplied by these differences in the concentration to describe these different operating conditions. Okay. And you don't need to understand that in a lot of detail. So know what absorption is, know a little bit about the Henry coefficient, and in the tutorial you'll practice doing this mass balance, and that's enough. And I just want to point out that there are some different devices, and I want to show you a couple of details related to those. So chemical absorption, the devices work the same. In this case, there's some chemical reaction that occurs in the liquid that helps to increase the rate of absorption and help the liquid to hold more gas. A really frequent additive is alkali. Alkali just means a chemical base, and these alkalis could include lime, soda ash, sodium hydroxide. These make a lot of OH minus ions, and they're dissolved into water. And this will then react with these acid gases. So we'll neutralize them, and we'll make it pretty efficient to get rid of them. So this can be used for these acid gases, SO2, HCl, HF, H2S, and CO2. And yeah, this is sort of the topic of my research, but there is an enhanced absorption. When you add this chemical reaction, it will help the liquid to hold more of the substance, but it will actually increase the driving force for this transport. And so this will increase the rate of mass transport. And for this reason, a factor, the so-called enhancement factor, can get added to the equation. Okay, there's some different devices that can be used then to contact gases and liquids. For instance, a bubble column is simply a column filled with this liquid, and the gas is introduced through a sparger at the bottom of the column and is rising up through the liquid and reacting with the liquid. And I have several bubble columns in my lab. To increase the surface area, the bubble column can also be packed with different filling material. This then reduces the volume of liquid that's available here, but it does increase actually the contact area between the gas and the liquid. This interfacial area, this is a really important aspect of these contactors. Another device is a spray tower, and this is actually used quite commonly in air pollution control to handle large amounts of gas with a smaller amount of liquid. And here's as packing material. You've probably seen this in other lectures, but to increase this interfacial area, there are some different types of packing materials that are available. So at the end, I wanted to show you one video from my lab related to the interfacial area. So I hope that you're able to see my screen and see a YouTube video. And here you actually see okay, so here you see in my lab I have two bottles, and they are, the gas that I'm running through them is carbon dioxide, just because it's not poisonous and not as bad as SO2 or H2S. And it's being introduced into gas washing bottles that are filled with sodium hydroxide and an indicator. So these bottles contain a pH indicator to show you how the pH changes as CO2 reacts with sodium hydroxide. So initially they're a base, which is blue, and at the end they're less basic and they turn yellow. And what I want to show you here is this bottle on the left. This is just has a glass tube in the bottom, so kind of like a straw. And on the right, it has a frit. So it has a glass disc which forms much smaller gas bubbles. And when I start this, okay, I have the gas running through and I've controlled it's the same flow rate. But here I have lots of tiny gas bubbles, and here I have lots of big ones. And you can see that the container on the right is changing color at a much faster speed than the device on the left. So that's the importance of interfacial area on gas-liquid reactions, which is the topic of my research and my habilitation, which I'm working on at the university. And that's all for today. If you have any questions, then I'll stick around for another minute or two, or you can feel free to write them in the chat.